What up guys, it's your boy, Fematica2, aka Young Galois, aka Quantum Chill, and today we're actually going to be solving another ODE, this one right here. The nth derivative of y is equal to x to the n. It's a quite nice one, I think. It's simple, it's general, it's elegant, it's a family recipe. Anyway, our n here is an element of the positive integers, because otherwise it just it wouldn't work out that nicely. So anyway, let's cut the shit. So first we're gonna be doing this two ways. Not first. We're gonna be doing this two ways. First one is gonna be the standard way. The second one, spoilers, is gonna be a superior way. I'll keep that as a surprise. So first, of course, we're gonna want the homogeneous solution to equal to 0, right? That's cool. And then, of course, we're gonna let yh equal to e to the lambda x, you know. Now, when we differentiate that n times, of course, it's just gonna be lambda to the n, e to the lambda x, hope you can see why, and we want that to be equal to 0. But since e to the lambda x is strictly non-zero, again we conclude that lambda to the n is equal to 0, or that lambda is equal to 0 multiplicity n. Right? Because if you have repeated roots, or a double root for example, you'd have lambda is equal to 0, or lambda squared is equal to 0, so lambda is equal to 0 multiplicity 2. Hope I'm making sense here. Yeah, anyway. So, in the example where we have lambda squared is equal to 0, our homogeneous solution would look like this, right? See? If we have lambda squared, then on a second order differential equation, we would have a constant, since e to the 0 is 1, and then another constant, but to keep them linearly independent, we would tack on this x. So it becomes a linear function. And with higher order differential equations, we would just multiply another constant by x again. So we'd have plus c3x squared, and so on. Like that. But here, since we're doing this n times, and we have multiplicity n, then our homogeneous solution is going to be equal to a polynomial. So we'll start with a0 plus a1x, right? So we're actually stopping at n minus 1. Hope you can see why. a2x squared plus a n minus 1 x to the n minus 1. Just like as in the other example, we would stop at a power that's 1 less than our multiplicity. So that will be our homogeneous solution, but we can express this as a series, so yh is going to be equal to the sum to n minus 1 from m is equal to 0 of am x to the n. So that's going to be our homogeneous solution. Cool, nice. Now, what next? Oh, yes, the particular solution.
Oh yes, kill me.
So we're gonna let y of p equal to... Now, this one's gonna be a little...
I'm so lonely.
You're gonna have to think a little bit about this. b0, using p now, xd, b1x, because if we differentiate this n times, we want this to be equal to x to the n. So, you'll see where I'm going with this. Plus x squared plus b2n x to the 2n. Because since this is our last term, when we differentiate this thing n times, we want this term to reduce to x to the n. when we differentiate the n times, since 2n minus n is n, times some constant, which is this b2n. So we're gonna actually want to determine what this is. All the other constants, we don't have to care about them, you'll see why. So, as an example, if n was equal to 2, so we would want x squared, then our particular solution would have to be of this form, ax plus a2x squared, I'm using a again, it's whatever, plus a for x to the 4, right? Because y prime, p, is then a1 plus 2a2x plus, well, I don't know why I did dot. What the hell? I'm done. X, a3, x cubed. So 3a3 x squared plus 4a4 x cubed, and so on. And in the second derivative, in fact, I'll write it down. I'll rewrite it. We just have the a1 term disappears, so we'll be left with 2a2, then plus 6a3x plus 12a4 x squared. See? And we'll have the x squared term right here. And if we want that, in fact, to be equal to x squared, we conclude that this a2 and a3 must be equal to 0. So, in fact, we would be left with that our a4, so, just gonna finish this example here, a4 is equal to 112. You see, because 12 times 112 is 1, and we would get exactly x squared. That's just an example. So, remember our thing. So when we differentiate this n times, all the b's would vanish, and the ones that would stay would vanish anyway. So the only thing that would be left with is this long chain of multiplication. So starting with 2n, right? Then 2n minus 1. It's just an application of the power rule. Dot, until n plus 1, right? So that we remain with an x to the n term. b2n x to the n, right? But I don't like the way this is written, so I'll rewrite this a little bit so that we can start with n plus 1. So starting with n plus 1 times n plus 2, right? Until n plus n, which is 2n. b2n x to the 2n. Cool. So it's almost like a factorial, but we're stopping here. It's like a rising factorial, actually. Here it's like a factorial, and here it's like a rising factorial. So we can express this as a product sequence. So let's do that. yp n. So product to n from r is equal to 1 of n plus r. b to n x to the 2n, and we want that to be equal to x to the 2n. Or x, wait, hold on, x to the n. I don't know what I'm talking about, I'm sorry. I'm always bound to make some mistake here, right? But look at this. You know what's coming. You know what's coming. You know there are markers coming, right? Like, bang, bang, get out of this house. And so, we conclude that our b2n is equal to the reciprocal of this product sequence, n plus r. Nice! But now remember what our particular solution was, or the form. A bunch of constants, it was a long polynomial of degree 2n. And since we concluded that all the bi are equal to 0, except this one's not. So, in fact, our particular solution is then equal to x to the 2n over this thing. Yeah! Alright. Okay. Well, that was that. It's a really nice little term here. So, yeah, let's get the general solution. If I still remember what the hell it looked like. So we conclude that our y is equal to, I'll write the particular solution first, because why not? Fight me. Right? N plus the homogeneous solution, which was this series. To n minus 1, n equal to 0, a n x to the n. Hell yeah. Nice. You know what? This one actually looks pretty good. I actually like this solution quite a bit. Even if it is just a polynomial. Anyway, that's that for the first method. Now, here comes the second method, which is so much better. It is. My blue marker, yeah. So we can write this in a different way. So we can actually say that this is d and y is equal to x to the n. So now we're writing this in terms of the differential operator. And we're applying it n times to y to get this x to the n. And because the differential operator is a linear operator, we can apply the inverse minus n to this dn y, which is just because, again, it's a linear operator, so it works additively. So we'll get d0 y. And this is equivalent to just doing nothing. So we just get y. And so our y is equal to d minus 1 x to the n. Ooh. Now, what the hell is this term? What is this? What is this? Well, might not be so clear, but if you recall that we defined d1 to be just the ordinary first derivative, then the inverse, d minus 1, is just the integral, right? Make sense? Cool. And so what we're actually doing here is we're integrating x to the n times. So we're actually doing this. X to the n, dx, 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 dot 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 dx. So we've got n of these integral signs and n differentials. And each time we integrate this once, we're gonna have n minus 1 integral signs and n minus 1 differentials, and so on. It's gonna keep decreasing until we get out of this nested integral. So I think we need to establish a pattern, because n can be arbitrarily large or small, but it can be arbitrarily small. But anyway, let's look at the first case. So we're integrating x to the n once. And all we're going to be doing is just applying the reverse power rule, but multiple times. So it's just going to be x to the n plus 1 over n plus 1 plus, remember, some constant. I'll call it k1, because there'll be a lot of these. N of them to be exact. Now, that's the first time we're integrating. If we do this 2 times, right? So we're just integrating what we got before again, dx. dx, it'll be n plus 1 times n plus 2, like that, x to the n plus 2, plus k1, I don't know if I'll have enough space, x plus k2. Do you see? And each time we integrate, we get a new constant. A new free constant, or, you know, whatever. So I'll just show it like a couple more times to really make you see the pattern here, for those who don't see it immediately. So let's start here. X to the n dx dx dx. Remember, we're doing this n times. So we want this index up here to reach n plus n, right? Until 2n, in fact. Isn't that interesting? So when we do this 3 times, it's of course x to the n plus 3, n plus 1 times n plus 2 times n plus 3. Look at that little product sequence here for me. It's interesting. Again, bit of a rising factorial. Plus, now we're integrating the k1x term. So we'll have k1 over 2 x squared plus k2x and plus k3. So we'll have a 3 here. When we integrate 3 times, we'll have the last constant we'll have an index of 3. Yeah, cool. Jesus. Right. I'll do it again. One more time to really drive the point home. So I'm not even gonna write all these dx, blah, 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 blah. Seeing what happens to this first term, right, is quite easy. n plus 3 might be a little small, the writing, but I think you can understand. X to the n plus 4, right? And then plus, we have our k1. So now it will be k1 over 6. But what's 6? That's just 1 times 2 times 3, right? Plus, now our k2 will be squared. k2 x squared, which again is a 2 factorial. Plus k3 x. k3 is then 1, which is 1 factorial, right? You see? I'll just rewrite it for clarity. Come on, a little bigger. 3 factorial x cubed, 2 factorial, and then our k4 over 0 factorial. Hopefully that's clear. Hopefully you can see that. Probably not. And so we'll have this descending, each term will be divided by factorial. 1 less than the previous one. And so our y, hopefully if I do this right, will then be x to the n plus n, right? Or x to the 2n. And yeah, again, it's familiar, isn't it? R equals to 1 of n plus r. Because we would be stopping at n plus n once again. And now, we had all these factorial terms. So we'd have this series. Okay, that's not a series, it's not a sigma. Okay, that's a little bit more like a sigma. Until n, like I, let's do I is equal to 1 of, so k I n minus I, right? Factorial x to the n minus I. N minus I, not 1. Okay. So, actually, this is our solution now. But I don't know, man, this term seems right, but this one, you know, how do we know that's equivalent to the series that we got before? Well, let's actually examine this thing. So I'll rewrite it again. Let's get a little bit more space for this boy. So sum to n, I is equal to 1, ki n minus I factorial x to the n minus I. So let's see. So that'll be k1 over n minus 1 factorial x to the n minus 1 plus k2 n over n minus 2 factorial x to the n minus 2 and I'll write it here plus k3 over n minus 3 factorial x to the n minus 3 plus dot 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 until, now what is our last term? It's until n. So this last term will be 0 factorial plus, so we have kn here over n minus n factorial, so 0 factorial to the x to the 0, so because x to the n minus n. So it's just plus kn, right? But we'd like to start from this kn, we'd like to start with a constant as we did before, so it becomes a little clearer. So if we start like that, if we start with kn over 0 factorial, x to the 0, plus kn minus 1, or in fact we could do k0, but you know, yeah, let's do k0, how about that? k1 over 1 factorial x to the 1 plus k2 over 2 factorial x squared and so on until kn minus 1, right? Because before we started with k1, but now that we start with k0, we're not going to end with kn, but kn minus 1. You can verify that yourself. Over n minus 1 factorial x to the n minus 1. Which is exactly the same as this then. But we can then rewrite this. So we're starting with the k0. So we will have a sum up to n minus 1 now from I is equal to 0 of ki over I factorial x to the I. But hold on, this is actually equal. That is not a sigma. Holy crap. That is a sigma. To our homogeneous solution from the first method. From m, or I mean the m like index, it's arbitrary. It could be whatever. It could be Hebrew, it could be Gaelic, it could be whatever spider language letter you want, but let's just keep them the same. Of ai x to the I. So in fact, using the second method, we've got a much clearer solution because our xi from the first method is just ki over I factorial. So, you know, it's just still a constant. Whatever this ki is, we're not going to be getting into that, but in fact, that is our solution. So let's finish it off with writing it down so I can cross it out. I mean, not cross it out, so I can cross it out because it's wrong. No, just kidding. So I can whip this bad boy out. So I can pull down my pants. Wait, what am I doing now? Alright. So, x to the n over this bad boy. This is probably my favorite part in this entire exercise, finding this term. Because it essentially is a rising factorial. Or at least what's known as a rising factorial. I learned about them just, yesterday actually, so it's cool. It's cool and epic. M plus r plus sum to n minus 1. Well, m. Yeah, let's do m. Or, let's do k for good. No, actually, yeah, that's... We're not doing k either. We're not doing that either. Let's just do I, 0 of ki over I factorial is to the xi. And one more detail before we
finish this up.
We know at least that k0 is equal to 1. So, yeah. Woo! We're done. We're actually done. Finally, after years, I've actually made another one. So that's that. Yeah. Sorry. Yeah, that's done. We're done. So that's it. So thank you for watching. Make sure to smash that, to crop that like button if you're up, if you're awake during real math hours. And yeah, I've been Thematica2, aka Yangalwa, aka Quantum Chill. So yeah, up until the next one. Peace.
And I can remember these words just off the top of my head. You've got cock, beta, omega, soy boy, and incel.